Hi everyone, this is Miss Lasar. Welcome to the Soil Degradation Lecture. So this lecture has two components. First, soil erosion, and we're going to talk about 4 different kinds of soil erosion. And second, soil degradation, and 4 major types and methods of soil degradation, along with how to prevent that soil degradation. So first, erosion. The thing I want you to be thinking about right now is how delicate soil is. I can't impress this upon you all enough. Soil takes an incredibly long time to generate. New soil forms about 1 centimeter every 500 years or so. That's how long it takes for our plant material to be sufficiently weathered down, our rock parent material to be sufficiently weathered down for our organic material to be broken down and then build up a thick enough layer to generate a centimeter of soil. It takes about 500 years. Soil is a super delicate mixture of ingredients. Removing ingredients like nitrogen and phosphorus, adding toxic ingredients, or removing topsoil entirely leads to unusable soil. And what do we need soil for? To grow all of our food in. So that would lead to an agricultural and economic collapse. And I'm starting with something kind of intense and serious because the state of soil across the world is actually fairly intense. This is one of the most immediate environmental crises that we need to deal with. So, in terms of soil degradation, soil injury, one thing we have to think about is just the loss of topsoil, soil erosion. How are we losing soil from the surface of our ground? There's 4 main types of erosion: wind, water, glacier, and coastal erosion and deposition. I'm going to go into each of these in a little more detail. Wind erosion is just what it sounds like. We have winds that are blowing over an area, and the wind is able to blow the soil away from where it started. So, the cause of wind erosion starts with a windy climate. Areas like the central plains of the United States, that are very windy regions normally, are absolutely at more risk for wind erosion. But there's another ingredient that's really important here: exposed soil. If your soil is covered, like you can see here in this bottom picture of a native prairie, this is in the Great Plains in the Midwest United States. If your soil is covered, the wind doesn't have anything to grab onto. If your soil is uncovered, you can see here a dirt road. You can see a little bit of exposed soil here in between these plants. That is exposed soil that can be blown away. A lack of native vegetation corresponds to exposed soil, right? So why would our soil be exposed? Because we removed all of the plants that were in there, all of those native plants with deep roots that help hold the soil all in one giant pack that's not able to be blown away by the wind. And we have a lack of cover crops. We don't have anything being grown on the soil, even a crop that we just artificially brought there to cover up the soil and prevent it from being blown away. Sandy soil makes us more at risk for wind erosion. Think about why. Sand particles are larger. They don't hold on to each other as well as clay particles do. And so you've seen this, you know this at the beach. It's easier to blow around sand. Sandy soils will definitely be picked up by the wind. How do we prevent wind erosion? It's really simple. Cover your soil. And we want to keep native plants in place. Native plants tend to have deep roots that are well adapted to the type of soil and do a good job of holding all of the soil into a solid mass that's not easily blown away by the wind. What about water erosion? You can see here some different pictures of water erosion. This is called gully erosion. So we have water flowing through the same area over and over and over, digging out a deeper and deeper channel every time. Our land might collapse a little bit as some of it is destabilized from the water flowing over that one region. Here you can see water erosion along a stream bank, exposing all of the deep roots of this tree. And here you can see a flood event that is likely to cause water erosion. And you can kind of see it in action. You can see how this flood is like washing away some of this topsoil right here. So what's the cause of water erosion? Poor water management in a flood zone. If we've got water running over our agricultural fields, we have done something wrong. Even if we're planting in a flood zone, we can do a better job of setting up our irrigation systems and our drainage systems to maximize our drainage if we're in a flood zone. Um, you can see here, this is in Tennessee. This is in a fairly rainy region of the United States. And this field does not have a good drainage system. Removal of native plants can also lead to water erosion because, just like in wind erosion, anytime we've got uncovered soil, we're at risk of erosion. All of the soil that's exposed between these rows of crops, that can be eroded. All of the soil that's exposed here along our stream bank, that can be eroded. Native plants hold that soil in place and protect it from water and wind erosion. Removal of wetlands. Wetlands can prevent floods from happening, even inland floods. And so removing wetlands increases our risk of flood. Paving of surfaces does the same thing. If we're doing a poor job of managing the water flowing off of our paved areas, we can end up funneling a lot of water onto unpaved areas with exposed soil and leading to our soil being washed away. And a rainy climate, of course. If we're in a region with a rainy climate, we're going to be at risk of water erosion. So one thing to think about with water erosion, and I wasn't sure where to put this, it's not really a cause, it's an effect. An effect of water erosion is water pollution. 3 different types of water pollution. Sediment pollution from, look at all of this sediment, mud that's being washed off into the water. That sediment can drown ecosystems, aquatic ecosystems. It can cover them in sediment. Nutrient pollution, as we wash the fertilizers that were on this field into bodies of water, or pesticide pollution, if that's what we're washing off of our fields. So how do we prevent water erosion? Maintain our native plants and wetlands. Maintaining our native plants keeps a cover over our soil. Maintaining our wetlands maintains a flood barrier. Proper land management and flood prevention, especially for urban or suburban areas with a lot of paving. And then what do we do if we have a bunch of water erosion already? So that picture I showed you before, this one, again, this is gully erosion. I'll show you that term in a sec. So these deep gullies that are formed from season after season of water erosion, those need to be reclaimed. So we need to fill in that land, essentially. We also need to think about how to minimize our water pollution. Even if our land is covered, we're probably going to have some water erosion bringing sediment and nutrients into our nearby freshwater ecosystems. We want to minimize our water pollution with wetland restoration so that those nutrients and sediment can be absorbed by a wetland before we reach, say, a freshwater river that's more delicate, or by adding something called a buffer strip, which is literally a strip of vegetation that's added around your agricultural area to essentially absorb all of the sediment and nutrients and pesticides that are being washed off of that agricultural region. Really, what we want to think about is prevention, though. Maintain our soil cover, maintain our wetlands. Glacial erosion is a little different. Glacial erosion is not human mediated. Glaciers that used to cover a large portion of the continents on Earth and now cover a much smaller footprint, move very, 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 very slowly. If you're not familiar with glaciers, they are giant mountains of ice that very slowly move by gravity over land. And because of their size and their mass, they scrape off everything in their path and they just leave behind bare rock. So, this is actually where new soils are formed because you know what's going to happen here, primary succession. The newly exposed rock will start to have lichens growing on it first, then mosses. Eventually, we'll have a thin soil layer build up and we'll have some grasses move in, etc. And we'll very, very slowly generate soil over time here where these bare rocks have just been exposed. So why do we care about this glacial erosion, glaciers scraping off all of the soil and vegetation that's underneath them? Well, a couple of reasons. First, soils that are formed after glaciers receded are fairly new. So, when we're looking at a worldwide distribution of soils, the regions that have had the glaciers recede most recently, so that would be like northern Canada, northern Russia, and Europe, um, those soils are fairly new, and that means that they are more nutrient rich. Soils close to the equator in our tropical rainforests, Those are extremely old. The last time a glacier was there was when the continents were in an entirely different configuration. And so, since those soils are so old, they don't have new minerals being returned into them from new parent rock material, which means that our oldest soils tend to be more nutrient depleted than our newest soils. And we can tie that into glacial erosion in terms of the timing of where do we see new versus old soils. Another thing that we'll talk about later in the course is the formation of valleys, canyons, and lakes from glacial erosion. These will be relevant later, especially the lakes when we're talking about freshwater ecosystems. Coastal erosion is our next type of erosion. Our cause here is tides and waves. You can see here a highway, an incredible example of coastal erosion. This has been eroded from waves. So you can see how the waves will come up, will dig into this bank, and will carry sediment away with them. So there's another thing going on here. In the bottom picture, we're kind of seeing the continuation of erosion because in these cases of coastal erosion, we're carrying away huge amounts of sediment into the water. We also have rivers that are depositing huge amounts of sediment into the water. And so we have in our coastal zones an extremely fluid um, situation where sediment is being built into new landforms. You can actually see one here constantly. And sediment is also being eroded off of those landforms constantly. It means that our coastal zones are incredibly dynamic and in another way of thinking about it, incredibly fragile. They're constantly changing. So, how do we prevent coastal erosion? Because we don't care that our worldwide ecosystems are incredibly dynamic. We want to build our beachfront houses and towns and cities and have those be stable places to live. How do we do that? We need to first maintain our estuaries and our wetlands. They are the first line of defense against wave erosion. They absorb floodwaters and will prevent a ton of wave erosion. We also need to maintain mangrove forests. Those also absorb wave energy in more tropical latitudes and maintain dunes, natural sand dunes. You can see some of them kind of in the back of this picture over here. But once again, those dunes are not just piles of sand, they're piles of sand that are stabilized by the deep roots of the plants that grow through them. And just like before, those roots hold things in place. We need to maintain that root structure because that will help to stabilize our delicate, fragile sandy dunes. We can also do some man-made techniques like jetties and sea breaks to prevent wave erosion. So jetties are long lines of rocks or other building material that you stretch out into the ocean, and you try to do it roughly perpendicular to where waves are coming in so that you can absorb some of that wave energy before it hits your more delicate landmass. And then the final tip for prevention is don't build near sandy beaches. Coastal erosion is a fact of the dynamic life on planet Earth. We're not doing so well with this last tip, so we'll see how that goes. Our next type of soil erosion has to do a little bit more with the effects of soil erosion. So, deforestation is a major driver of soil erosion, and there's a positive feedback loop at play here. The positive feedback loop starts with removing trees. Once we remove trees, we are, of course, exposing the soil that was previously around them. So when you remove trees, it's really hard not to remove everything else that was on the ground, like all of the leaf litter that was there. We also kill the trees when we remove them. And so we're exposing our soil and our roots deep underground are dying, which means that they're not going to hold onto the soil as much. They're not going to maintain water in the soil as much. And we're going to start losing our soil that's now exposed and a little drier to wind and water erosion. That means that as we lose our topsoil, we are losing nutrients, we're losing our water holding ability, more trees will die, more soil will be exposed, more erosion will happen, and the positive feedback loop will continue. Our second section for today is topsoil degradation. We're going to talk about three Major methods of topsoil degradation. So this is we keep our soil in place, but our soil becomes unusable. There's three different major issues here: salinization, desertification, and waterlogging. First, in case you're thinking to yourself, I don't really care how soils are doing right now. This is a map that shows soil stability worldwide. And what you can see from this map is that any region in blue or red is a region where there is concern for the stability and nutrient availability of the soil. And that is covering the majority of spaces on Earth. We do have some stable regions. What do you notice? These stable regions are absolutely in less populated regions. And then we've got some stable regions here that are actually just non-vegetative. This is the Sahara Desert, and we are not growing enough plants there to consider it a region with soil. But of the regions with soil, look at all of the swaths of some concern over soil stability in blue or serious concern. There's one other thing that we just need to be on the same page about. That is what a water table is. So the water table is the level that groundwater reaches. Underneath the ground, there is groundwater that is constantly accumulating in the rock layers deep beneath our feet. And what I hope you can see from this diagram is that our land rises above the water table, but then our water table will be exposed anywhere that our ground dips below that level. And so if we do something to raise our water table, then all of a sudden water will be higher up and closer to the surface of the ground. If we lower our water table by, say, overpumping the water table, then our groundwater drops. Plants sometimes have roots that are deep enough to access this groundwater, and that's going to be important in a moment. You can also see how these regions that are close to this lake, for example, this region has a shorter distance to the water table than like this region over here that's vertically a little higher up. So when we think about access to the water table and who's got a shorter distance to the water table, these guys have a shorter distance to the water table than this region. Okay, with that in mind, let me tell you about salinization. Saline, salt, this has to do with salt. So salinization is a result of over-irrigation. And before I talk about the specific causes, salinization means exactly what you think it means, a buildup of salt in soil. Can plants grow effectively in salty soil? Absolutely not. So how does this happen? How do we get a buildup of salt in soil? Well, the first key is over-irrigation, putting too much water on your crops because you didn't maintain your soil properly. When we over-irrigate, which is a traditional move in most industrial agriculture, almost every industrial farm nowadays over-irrigates their crops, we have water saturating the O, A, and B layers of the soil. So the top layer, which O probably isn't there in a farm, the A layer, our topsoil, and then the B layer, our subsoil. When we saturate our B layer, and we also have water stretching up into our A layer, dissolved salts that are in our B layer, remember there's a ton of minerals in our B layer, dissolved salts from our B layer can actually migrate up through capillary flow. That's kind of what you're seeing in this picture. So we've got our topsoil here with our roots in it. Down here we've got our minerals that can be dissolved. When we over-irrigate, these minerals can actually flow up because there's now solid water all the way through here. And when these minerals flow up, they get left in the top of the soil, and they don't move from there. They don't go down from there. So we have a buildup of salts in the top layer of our soil. Our water that came up here evaporated, but our salt gets left behind. Additionally, a really common cause of irrigation is, a really common cause of salinization is irrigation, over-irrigation, that just dissolves straight from the surface. So we over-irrigate our field, water is pooling on the surface for a little bit because we've over-irrigated. That means giving our field too much water, more water than it needed. And that water that's staying on the surface evaporates, and it's not pure water, there's salts in it, it leaves those salts behind. So what you can see here is actually an example of this situation. We had irrigation lines that were stretching across this field, and over time, the water from those irrigation lines evaporated or sank deeper into the soil. The salts that were in it were left behind when the water evaporated. There's a couple things that will speed up salinization. High temperatures and exposed soil are the two big ones. The hotter it is, the more evaporation. So the more salts will be left behind because of that evaporating water. And the more exposed soil, again, the greater the likelihood that water will be evaporating straight from the surface. Exposed soil tends to be hotter, water will evaporate faster. And finally, high porosity soils like clay are at risk of salinization because they hold onto water so well, which means that it's really easy to over irrigate your field. You water your field, and because it's a clay soil, water isn't going through so quickly. It's staying there near the surface for a while, and it has time to evaporate and leave the salts behind. How do we prevent salinization? Don't over irrigate your fields. Our next soil degradation threat is called desertification. And students tend to think that this means a field of soil becoming a desert, and that's a decent way to think about it. It's got a slightly more specific meaning. Desertification has to do with a loss of soil productivity. You've hit desertification when you have lost soil productivity by 10% or more. So that means your crop yield is reduced by 10% of what you would expect. And desertification is a combination of a drought and that loss of soil productivity. So what's causing the drought here? It could be climate change. It could be just coincidence and natural fluctuation of climate cycles. Climate change is accelerating or is increasing the length of droughts that we see, and is increasing their intensity. So climate change is a major driver of droughts worldwide right now. What's causing the loss of soil productivity? Well, that would be like a loss of nutrients. Industrial farming practices, especially monoculture, growing the same thing in a field, just the same crop item over and over and over, that is associated with a loss of nutrients because that crop item, all plants of that crop item are taking the same nutrients out of the soil, and they will deplete those nutrients out of the soil pretty quickly. A loss of topsoil from erosion will also accelerate desertification. When we lose those nutrients, we are rushing toward a loss of soil productivity. When coupled with a drought, we have desertification. And sandy soils are at risk of desertification just because they're so vulnerable to wind and water erosion, which we know leads to a loss of topsoil. So how do we prevent desertification? So the main techniques here are traditional agricultural practices. Things like leaving fields fallow. This is a fallow cornfield. You can see some exposed soil here, so that's not fabulous. But what you're seeing here that's good is a bunch of dead corn. After you use your field to grow your crop of interest, the best technique is to leave all of the stalks, all of the dead bodies of the plant parts that you don't care about in your field, and let it decompose over the next 5, 10, 20 years, depending on what crop is busy decomposing. That's called leaving your field fallow, and that will allow the nutrients that are in all of these corn stalks to be returned to the soil, and we won't be removing them from the soil. Allow time for soil regeneration, allow time for that decomposition, and time to return those nutrients to the soil. Cover crop. This is a cover crop. So you can see we've got corn again, one of our major crops here in the United States. And in between all of the rows of corns, you don't see as much exposed soil as you would expect. What you do see are a bunch of weeds. They look like weeds. These are intentionally planted weeds. These are called a cover crop. The job of a cover crop is literally to cover up the empty soil so that you do not lose that precious topsoil to wind and water erosion. And I know it feels weird to plant something in your field that could conceivably steal the nutrients from the soil that your crop of interest should get. But what do you think you do with this cover crop? You just let it sit there and let it decompose eventually back into the soil. You don't let it remove all the nutrients by removing this crop and burning it. You let it decompose right here in the field so that the nutrients that it's removing from the soil are then returned. And here's another strategy. This is called polyculture. I started by saying that monocultures, planting all of one thing in a field, remove nutrients from a soil quickly. Polyculture allows you to have things in your field like legumes that actually return nutrients to the soil. You guys all know that legumes, bean plants, can fix nitrogen and can add nitrogen back to the soil. Polyculture, growing more than one thing in a space, will allow that to happen. There's many other benefits to polyculture. We'll talk about that in a later unit. Desertification is a major issue. Here in the United States, our Great Plains is under moderate threat to severe threat of desertification. We have many areas of very severe desertification worldwide. Take a look at this ring around the Sahara Desert. Some people like to talk about the Sahara Desert getting bigger. It's getting bigger because the agricultural lands on either side of the Sahara Desert are fairly rapidly being desertified. Our next soil degradation threat is called waterlogging. So, quick recap of how plants breathe. Plants actually absorb a lot of oxygen through their roots, and it's really important for terrestrial plants that their roots are exposed to air spaces because oxygen is found in those air spaces and roots need oxygen. Otherwise, the root cells will die and then the entire plant will die. If you flood a field with water and you fill up all of those root spaces, you are preventing your plant roots from getting access to oxygen. There is very little oxygen in that water, and what's in there will be depleted quickly. So if we flood a field and we don't allow it to clear out quickly enough, if we keep our roots submerged in water for too long, we have waterlogged our plant, our roots will die, and then the plant will die. So how does that happen? Over irrigation again. And now we come back to the water table. So if we raise our water table through over irrigation, through adding too much water to our soil, and our water table gets high enough, it's going to naturally surround the roots of our plants. They will be waterlogged and they will die. We can also have this happen in a place where we just have a naturally low water table. So just remember that there are some regions that are closer to the water table than others, some regions that are closer to sea level essentially than others. Those are regions that would be more at risk for waterlogging because it won't take very much irrigation to raise that naturally low water table to the surface. Poor drainage and a rainy climate. So if we've got poor drainage and a rainy climate like you see here, you can envision a situation where our field floods. And maybe it's a clay-rich soil with poor drainage and we have more rain forecasted. We can absolutely have waterlogging. High soil porosity, high water absorption, clay soils are more at risk for waterlogging. And a lack of native plants. Our native plants typically have deep roots and large root systems that do a good job of effectively clearing the water out of the soil quickly. How do we prevent waterlogging? Don't over-irrigate. And better water management if our water is coming from surface runoff, for example. Maintain those native plants, use them as flood prevention. Don't over-irrigate is really the key here. So if you were going to take two things away from this lecture, I want you to remember to cover your soil and protect your deep roots. Don't let it blow away. Don't let it be washed away. Keep that soil in a firm, nutrient-rich bundle. Thanks for watching all about soil erosion and soil degradation.